Hello, everyone, and welcome to today's MIST seminar. So today we have a seminar from Teuber Coburn, and Jessie is a research fellow at the Mullard Space Science Laboratory, University of College London, working with Professor Christopher Owen and Dr. Daniel Versaren. Jessie's PhD was at Queen Mary University of London with Dr. Christopher Chen. So today Jessie's going to give us a seminar on velocity space methods for spacecraft observations. And just to make everyone aware, sorry, I forgot to say at the start that this seminar is being recorded. So maybe keep your camera off and stay muted. So yeah, thank you, Jessie, for giving this seminar today. So we'll have your seminar now, and then we can ask questions at the end. Okay, thanks.
Yep, thanks for the invitation. I'll just also note, I don't think I put it in my bio, that I'm also a research affiliate at the Space Science Institute in Boulder, Colorado. I'm noticing a slight, I can't see my cursor on my own. These are things that we check, huh? All right, so I'm just gonna pull this over and I'm gonna do it this way, and I apologize to everyone, but I'm gonna need my cursor throughout this talk. I just want to mention as well that this work is done in collaboration with Joe Jung and then my two supervisors. And then, so I have a very ambiguous title. This is going to be a methods talk. I'm really going to dive into this analysis method and really try to show you, the operation of it. I'm going to show you some results. The results, of course, are going to be from spacecraft or applied to spacecraft observations, right? And so I'm going to do my best to make sure that I'm making it clear what the observations are that I'm using, but I am going to bounce around a little bit between the magnetosphere and the solar wind, electrons and protons, and I don't do any work with ions really in this talk, but the method is going to bounce around a little bit. So apologize if that's not clear to you, but really the focus is on the methods. And so I wanted to start by giving a background of the analysis technique, why I built it, what were the ideas that went into the creation of this method. And so really that starts the way to start this off is to take a step back and ask what the questions are at hand. And so the first one, I've just got my bullets here. So what processes mediate the interactions between a non-equilibrium distribution functions and turbulent electromagnetic fields, right? So we have a non-equilibrium, in terms of momentum space of the particles, and they're interacting with a fully nonlinear electromagnetic field. And then more to point a little bit more at like quantities, is what controls the heating, the acceleration of particles, and the emission properties of the plasma, right? So that's the game that we all kind of play. And those are the questions. That's a way to ask these questions, okay? And so I'm drawing on some inspiration. Okay, so these are two figures on the right-hand side. At the top, you have Servideo et al. 2017. What you're seeing, say in blue, is an isocontour of the ion velocity distribution function as measured by MMS. It's an average of the four spacecrafts. And so in this article, Servideo, he employs a Hermite expansion to describe the proton VDF, the ion VDF in the magnetosphere. And this Hermite expansion allows you to quantify, as I would say, fine structure. This was part of the inspiration for the technique that I'm going to show you today. Be able to describe beams and all these crazy structures, right? That's kind of the power of this technique, and the beauty of space plasma physics. In the bottom panel, I'm showing a plot from Chen et al. 2019. of the trace power magnetic field spectrum. These are the things that the turbines community obsesses over. In the bottom panel, you have the local slope. Okay, so you just take the slope of the or like the power law of the spectrum locally, and you move across, and you get this plot down here, and we all argue about what these alphas, what these power laws should be. But these two papers in particular, kind of issues that they addressed and things that they were able to do were the inspiration as to why I decided to build the analysis technique that I'm going to show you today. Okay. And so to get into this, let's take a step back. Let's remind ourselves of the equations that we know describe the full interaction. So I've put Boltzmann's equation for plasmas. Okay. So left-hand side is your Vlasov side. The right-hand side is Landau's collisional operator. I am going to be talking about collisions today. And so a good place to start is to take a look at the equation and then ask ourselves the important question: what is measurable here? So the electric field, the magnetic fields, right? They sit in the Vlasov side. Um, these are very well measurable. There's limitations, of course, on time and space resolution, and those are given by the instrument and the instrumentation, the number of spacecrafts. But in general, right, we measure these well. Okay, and then what about F? There's more severe limitations on time and space resolution. Space maybe not so much, but time resolution. And but not necessarily this, but velocity space is not necessarily more complex, right? We do this all the time. We've done this for ages. We've done it since the first spacecrafts that went out. And so these are our measurables. Okay. And so if you just wanted to get a direct solution to the above equation, say in terms of time, know what F will be at a later time. Of course, you need to couple this to Maxwell's equations, okay? But if you're looking for this, what is the most important thing? The most important thing is or are gradients of F, okay? So our gradients are F sit here. So velocity space gradient, right? This mediates the electromagnetic interaction. This is the free streaming term. You get a spatial gradient. And then up in the collisional operator, we have these velocity space gradients that mediate particle-particle collisions, okay? So these are the most important things to measure, okay? That's my argument. All right. So let's take a look at what spacecraft measurements of the VDF and of these gradients look like. So this particular set of slides, I'm going to be showing measurements by the electron analyzer system, which is part of the solar wind analyzer on solar orbiter. So this is solar wind measurements. You can find all the instrument details in Own It All 2020. What I've done here is I've just put the accumulation time and the availability of these VDFs, right? So there's a nominal trigger that the trigger just changes the availability, and then there's burst mode, right? So this is very fast for solar wind. For the magnetosphere with MMS, maybe it's not so impressive. But you know, time is a time relative to this time scale, right, relative to the time scales at which we're looking at the distribution function is really what is important here. So I've put the electron, a typical electron cyclotron frequency in the solar wind here. So 10 to the 2, 10 to the 3 hertz. This is much faster than what we're measuring the electron distribution function, right? So we really expect to be measuring very gyrotropic electron distribution functions. Okay, there's times when we maybe approach non-gyrotropic distribution functions, but for the most part in the solar wind, we expect these to be very gyrotropic. Okay, so the analysis method in a nutshell does this. It converts the instrument F, okay, to a cylindrical coordinate system. So that's up here. This is where we'll start. These black dots are just that conversion of just taking the center of these little of the bins, these bins being volumes in velocity space, and then I've put them as their perpendicular, so local magnetic field divided by the thermal speeds. Okay, and this nice plane here in this black semicircle in the middle is the portion of the VDF that's corrupted by interaction with the spacecraft, or they're from the spacecraft themselves. Okay, and so the second step is to interpolate to a new grid in V perp and V parallel. Okay, and then the final step is to low pass filter the VDF. Now, there's two big steps here. I'm really going to just focus on this final one. And we can talk about this. We need to talk about the second one, but it's more of like a sit down and talk about it and have a board in front of us. I'm happy to talk about the interpolation, but I'm really going to focus on this low pass filter. Okay, so the low pass filter, the way that this is done is really through the beauty of the spectral techniques. Okay, so the spectral technique works like this. Consider expansion. Take F, okay, I've just put it as V parallel. I'm just going to work in one dimension for a lot of this. Of course, you need to do this in multiple dimensions, and you start using different functions to do this for different geometries. But just for sake of a presentation, I'm going to just kind of work through this in one dimension when I can, to simplify all the stuff that I need to show. So you consider that F is approximately F sub m. Okay, F sub m has a coefficient up front, which involves the density and the temperature, and then you have your spectral coefficients, and then you have some nice functions that are orthonormal. Okay, so the m definition comes from the largest m that you consider. Okay, and so if these functions are orthonormal, then you can directly obtain the C sub m's, which are our spectra, just like this. Okay, where F is measured. Okay, and then the density and thermal speeds are down in here, so you need to obtain those through a moment technique. And so that's really the whole idea. Okay, obtain C sub m from F directly. Okay, and then come back up here and re-express F sub m this way. That's the whole idea. Now, one of the sets of functions that have gained a lot of popularity, and are very useful, are the Hermite functions. Okay, I've put a few orders of the Hermite functions themselves up here, and reason being the utility is well expressed through the n equals 0. Here, this is this pink one, or this red line here. It is a Gaussian or your Maxwellian function. Okay, and as you increase order, you get finer and finer structure. Okay, that's the two basic ideas that I think are important to get through all this. Now, the question to ask is, well, I use a spectral method. Okay, and so the first reason is that the derivatives of these Hermite functions, or these functions in general, they're much easier to handle, right? So if we come back to our question of what is most important here in terms of finding a solution, we have methods to describe the gradients. Okay, so I've just written out what the gradient of F of sub m is using recursion relations. Okay, so this should be a sum up to capital M. Sorry about that. But essentially, these functions follow a recursion relation. You can directly calculate the gradients. So if you know the C sub m's, which you obtain directly, you then can calculate gradients, and you can put these back up into your equation. You can use these as a method of solution. Okay, the same affordability of the recursion relation follows for the spatial gradient as well. Okay, so I've just gone through and I've used chain rule. So this n sub h has thermal speeds and densities. So if you know the gradients of the densities and the thermal speeds, you can and the thermal speed is in this definition as well. You have a method. Okay, I'm not saying that this is super fun, but at the end of the day, you do have a method, right? We do. So that's the idea. So let's take a look at what the analysis looks like. Okay. So, all right. So I'm going to go through a good set of slides on this. I'm going to use essentially the same convention. On the top, I've put the result of the interpolation. So this is F, raw F interpolated, okay, to a new grid. And then I put the results of the Hermite expansion, okay, where I solve for the C sub m's and then re-express it here, okay, in the bottom. I'm then going to use these little slices. Okay, so there's a slice in the perpendicular direction, there's a slice in the parallel direction, and then I'm going to plot them over here. Okay, and I'm going to do that the same for the Hermite expansion version of the VDF. Okay, now what is important is purple here. This purple or violet line is the interpolation, and then the green here is the result of the Hermite expansion. Okay, and then yellow is the base function. Okay, and so that's going to be the convention as I go through these next set of slides. So that's what we're comparing. You can see that the green line is the result of the Hermite expansion. The purple line is the interpolated function. Okay, and you can see that there's tons of structure and it's super bumpy. Okay, and you can see that in here in this as well. But you can see to a certain degree you're really grabbing the function. The purple function very, very well with the Hermite technique. Okay, this Hermite expansion. That's kind of the beauty of the technique. So now when we go to look at the derivatives, okay, so this is the derivative in the parallel direction. Okay, the parallel derivative of the interpolated function on the top, Hermite function on the bottom, and then I've done the slice thing on the right hand side again. What you can see is that the bumpiness in that in that derivative is expressed, or the bumpiness in the function is more expressed in the derivative of it. Okay, and so you can see that, right, the green line, the Hermite expansion is very bumpy. It's very bumpy here. This reflects the overall, say, like probably noise, right? Would be okay to call it that. I don't know. But the overall roughness of the function itself somewhere in there, okay? And so I'm going to do the same in the perpendicular direction. So this is the gradient in the perpendicular direction. It goes from down to up. And so you can now see this purple function here, okay? The interpolated function is very bumpy, and the Hermite expansion technique has grabbed that bumpiness very, very well, right? So that's great. Okay, we can get something, we can get F sub big M very close to our F. All right. Now, we're getting closer to reason two, right? So the spectral method provides a way to deal with noise and the resolution issue. Okay. Top panel on top left panel, I've put the 2D spectrum, okay, because I'm working in V parallel space, so I need a two-dimensional spectrum, and then I've taken that spectrum, I've normalized it by the 0, 0, the base function, okay, the power of the base function, okay, and that's the color. So what you see is most of them are very small. This is 3 orders of magnitude, and most of the power is here. Okay, that means that your base function is working, is at least near the function, but there is power out all of these. Okay, so let's go to a line plot. I've done a slice thing again. The slice thing is really useful. So the slices are here. Okay, and so what you see is you see power in low orders, and it decreases, and then it starts to flatten when you look in along both axes. Okay, so the idea is to truncate the spectrum or set a bunch of these to 0. Okay, and then take that inverse transform again, and have a representation of the distribution function that is low pass filtered. Okay, that's what I mean with the low pass filtering. That's what spectral methods allow you to do, right? That's the beauty of them. Okay, so I've redone all this business with the low pass filter. Okay, so again, we have this purple slice, which is our interpolated function, and then green is the low pass filtered version of the Hermite expansion, right? And so that's green here. You can see it here, and then yellow is our base function, right? So we see a small deviation from the base function, okay? And let's see, so that's the parallel gradient. This is the perpendicular gradient. And we've now we've now removed this huge spike that's here, and we start to so the game from there, right, becomes, is that real or is it not? Is it physical? Is this physics? Is it not? Is it an artifact of bad of a bad interpolation method? Is it an artifact of the limits of the instrument itself? And so that's the kinds of games that we can start to play. You'll see that the gradient gets very soft here. Okay. That's the result of some kind of like plateau. This is a plateau is a classic quasi-linear feature that we should see in the VDF. So now you can start to ask, right? Like, is this a real feature or not, right? So and I've kind of made the point already, but this is reason three, is that departures from VDS, such as Maxwellians and kappas, right? So the yellow is just a Maxwellian. Okay. The base function is Maxwellian. Departures from these functions are very simple to express with this method. Okay, so those are the three reasons. I have a super long slide on interpolation that I'm going to skip because it's a new discussion point that I'm bringing up in this talk. I'm going to skip that extra slides if you want to see it. So let's go drawbacks and current issues. The truncation of the spectrum is not straightforward. We need a general method for this. I kind of have to do it case by case right now. Well, some of the work I'm going to show you today, I'm not doing it case by case, but in general, which ones to set to zero and which ones to keep is not a super straightforward question. So I'm looking for general methods on how to do this. The method currently still requires an interpolation to V-perp and V-parallel. Okay, there's ways to skirt this, but they create lots of other issues that I believe make your end result not as trustworthy. So I'm not going to explore them so much. Again, extra slides if you want to see it. And then the final point is that the expansion is not guaranteed to be positive. Okay, I don't really have so many issues with this, but this is quoted in some papers that have tried these expansion methods before, but it is a drawback of the technique, is that the final f that you get out of this is not guaranteed to be a positive definite function, and f is positive definite because it is a probability in configuration and momentum space, right? Okay, so going forward, I've just showed you the technique, showed you an application of it, how it works. And so the outline from here is I'm now going to apply it to in the context of wave-particle interactions. I'm going to show results from a recent paper of mine and Chris and Daniel as well. And then I'm going to show you two sets of preliminary results. Most likely, I really think I'm probably just going to get to one of these just due to time issues. Apologize for that, but we'll see where we get to. Okay, so the results in the 2024 paper are more than just an analysis method, right? We really use the analysis method in there, but I want to give you the background context. I want to give you the physics, right? That's what we're here for at the end of the day. So I'm going to summarize Bertschich et al. 2020. Okay, so solar orbiter, the search coil makes observations of Whistler waves. Okay, those observations are quasi-parallel propagating waves. They're right-hand circularly polarized, and there's a quite a large frequency bandwidth in the magnetic field power spectrum, around like 25 hertz. This is about where we see them. So you're just gonna have to you're just gonna have to believe me that the checks on the waves were done. That's what we get. Now the important part for us, okay, or for us, meaning you guys and me today, is that the waves were cotemporal to a non-simple electron VDF. Okay, so when we saw the waves, we also saw an electron VDF that could not be simply expressed by like kappas and Maxwellians. Okay, maybe superpositions of them and stuff, but this is what I mean when I say non-simple. You couldn't just fit a Maxwellian and get a decent chi-squared and call it a day. And so what was this feature? Okay, I am going to really try to get through the description of this feature. This because it is a big part of the solar orbiter mission in terms of observations of electrons. Okay, so the feature that we saw is predicted from exospheric models. Okay, they predict a sunward deficit of electrons, right? So what is this exospheric model? What this does, it says. At the sun, you get pressure gradient acceleration of protons and electrons, just like Parker acceleration. Okay, and because electrons are lighter, they are accelerated to larger distances. That sets up an electric field, an ambipolar electric field between the protons, and there's plenty of ions as well. Okay, and the electrons. Okay, now the electrons see this electric field, or they feel this electric field as a potential well. Okay. So there's this potential well that's created, and this traps particles. Okay. This traps the electrons. So I've put some trapped trajectories here. Sorry, the ballistic trajectory here, ones that return to the sun, and then I've put some trapped ones here. Okay. So it's that well that traps them as they move away, and then as they return, they'll mirror just the magnetic mirror force, right? Some will escape. Okay, some will have enough energy to get past this well and escape. Now, the ones that don't escape, okay, because they're not escaping, if you use energy conservation and magnetic moment conservation, you find that that escaping population, okay, the result of that is a deficit. Okay, now I'm gonna show. Now, the deficit is drawn on the right-hand side. This is a figure from Birchich et al. 2020. So the way that these figures work is you see V parallel, you see V perp. The darkness of this color over here denotes the density, the phase-space density. Okay, and so what we've done is we've put it a little bit lighter over here than it is over here. Okay, so this is what we expect, and this is what we measure. There's some nice papers on this. You can look into the 2020 paper. Now, the importance is that this creates an instability. Okay, so the instability that this creates falls into the Whistler heat flux family. Okay, so we're going to compare the left and the right. The left-hand side has no deficit. Okay, and what we've done is we've drawn a typical phase velocity of a Whistler wave. Okay, yeah, the phase velocity, and then we've displaced the typical cyclotron velocity away from there. And if you then take a look at the shape of the VDF in that portion of velocity space, you see that the gradient, okay, going from high density to low density, diffusion process, that's what a diffusion process does. If you go from high density to low density, you have contours, or you would push particles that go to larger and larger total energy. Okay, the black dotted lines are total energy. Okay, so this process wouldn't happen unless there was energy there already. Now, if we take into consideration the deficit, okay, which we've done over here, these red lines, there's the possibility that the gradient in the phase-space density brings you in the opposite direction. Okay, so now you're still going from high phase-space density to low phase-space density, but look, when you travel along this way, you go from higher energy to lower energy, and so that's the ingredient, the key ingredient for an instability. Okay, so the deficit can cause an instability whereby electromagnetic waves are released at the expense of particle energy. Okay, and so why is this important? This is a gradient. This is a heat flux family instability. This controls the heat flux. The gradient of the heat flux contributes to the total thermal energy budget. So this is a process that can affect the total thermal energy budget of the solar wind. That's the importance. Okay, quite a lot of nice physics wrapped up in this 2020 paper and then in my 2024 paper. Now, we want to quantify this interaction with the analysis technique that I've already showed you. How are we going to do that? Okay, so we did this by taking using the quasi-linear equations, this framework right here. I'm not going to explain it to you. I am going to show the equation though, right? So this is the time evolution of F. Okay, so our background quasi-linear F. Okay, this is how it should evolve. It evolves according to a magnetic field energy spectrum which we can measure. Okay, and it evolves according to the wave frame pitch angle gradient. Okay, I've put the waveframe pitch angle gradient right here. You have gradients in v parallel, gradients in v perp, displaced by the phase velocity of the wave that you're considering of the distribution function. So the analysis technique that I showed you before, we're going to employ that analysis technique on F, okay, to get the evolution. Now, what we did in the paper as well is we quantified the change in the parallel heat flux. So how does that happen? I've just put it up here in a kind of like simple, easy, demonstrative way to see it. If you were to plug in the heat flux correct moment up here and integrate, you get how the heat flux will change, right? And so that was what we were going after. Okay, so to summarize Coburn et al. 2024, we saw Whistler waves co-temporal to a non-simple VDF. We used this Hermite expansion. I had to use the Laguerre functions for the perpendicular dimension. We use this expansion method to resolve the VDF and get a trustworthy VDF. Okay, and then we measured the growth rate directly, right? The growth rate involves your waveframe pitch angle gradient and the change in the heat flux, the rate of change of the heat flux. The growth rate I've put here. Okay, this is the measured growth rate. There's no electromagnetic field in here. This is just the VDF. Okay, and then I've done the Doppler shift to the wave number. Okay, and so this is the span in wave number space that we expect wave growth. And then if you take a look at the search coils measurement of the magnetic field, the trace magnetic field power spectrum, that's in this blue, and employ the same Doppler shift, you get a perfect matching in terms of this little bump enhancement of the magnetic field and the growth rate. Okay, there's a spectacular display of the power of this analysis. Okay, this is just VDF, this is just magnetic fields, and we get perfect correspondence between growth and where we see the waves. Okay, with 20 minutes left, what I'm going to do is I'm going to skip one of my preliminary sections, and I'm going to jump to some work I've been doing on collisions. Okay, so I think it's probably the second thing you learn about the solar wind, right? Is that the solar wind is collisionless. And you go through and you calculate a mean free path for a proton. You see that it's like on the order of 1 AU, and you say, okay, well, we probably don't need to worry about it so much. But I do see reason to reopen this question, and I am going to reopen this. And so the best way to do it is to go back to classic solar wind papers, go back to the literature, beautiful literature. So this is a Marsh and Goldstein paper from 1983. They're studying helios measurements, and they're looking at protons. Okay, and so the quantity that they study is this tau of V. Okay, and it's the deflection timescale to approach isotropy, and it's derived in Spitzer's book. Okay, and so this is the timescale at which you would expect the distribution function to isotropize if you have like a Maxwellian and a delta function, both protons interacting. Okay, now there is velocity space dependence on this timescale. Okay, and so what I've done is I've put I've written out the quantity here. Okay, there's this v hat, which is v over the thermal speed, and then you have like your Coulomb logarithm in here. These size are error functions, derivative of an error function as well. And so what I've then done, or what they do in the paper, is they then define this. Let's see, what's the best way to do this? Yeah, they define this N of V. Okay, so this N of V is proportional to 1 over tau of V. okay? But it's now it's now unitless because they've used the radial distance at which they made the measurements and the solar wind speed to come up with an expansion time, okay? Um, and then they've divided that expansion time by this expression of the time it takes to approach isotropy, right? Now, I've put it up here, okay, or in this plot, it's right here, so it's this black line here, okay, and so what this black line is doing is at the core, it's very, very large, um, and then as you move away, it gets smaller and smaller, right? And so this is the velocity space dependence of the collisional operator. Collisions are very strong when you're close to the plasma frame, okay, and they're weaker further away in the VDF. And this is a really important aspect of collisions, okay? And so to get a collisional time, to get a time in a mean-free path, you put in the thermal speed here. Okay, that's the classic one that we use, right? But it is really important to take a look at what this time scale is relative to, say, the expansion time for protons for a realistic VDF. And that's what they've done on the left-hand side here. So here, black dashed is the actual measurement of the VDF. You see a beam out here. This black solid line is a Maxwellian fit that they did. And here's the 2D version. So you see this beam, this parallel beam, which is almost always measured in the solar wind, right? This beam. And then, so what they've done is they've drawn these black lines at where n of v is equal to 10. Okay. And so what they're saying is that inside here, collisions dominate, and outside, the physics is collisionless. And so this is why I wanted to reopen this question, right? So why study collisions? So March's study relies on setting n of v arbitrarily to 10. I think they just found it to work well for their paper, okay? And then if you take a look at sophisticated versions of the collisional operator, you find that for finer and finer scale departure from the or fine scale derivatives contribute more to the collisional operator, okay? Or they have a larger contribution to the collisions. You can just take a look at the collisional operator itself and see that. And that's not captured in this Spitzer harm version, because Spitzer harm was working with a Maxwellian and a delta function, right? Okay, so it makes this time scale, kind of it's an ill-posed transport theory is an ill-posed problem. We all know that. Okay, all right. And so the next thing is we need to understand collisional heating and momentum deposition in general in the solar wind if we really want to close the problem, right? So there's portions of the VDF that are collisionless. There's portions that are collisional. We don't know that separation well. And both processes are contributing to heating and acceleration and drag and drift and all this kind of stuff. So what I've done is I've rewritten the collisional operator, Landau's collisional operator here. Okay, it evolves the velocity space gradients here onto F. Okay, it's got some complicated mathematical properties that make it beautiful. It is a convolution of two VDFs. Okay, and then you have this difference, this increment here, which forms this operator here, which is responsible for all these non-local interactions. Collisions are a very complicated interaction. Okay, and so my reason for bringing this up is that with a sufficient gradient technique, this operator can be measured, and the analysis technique that I showed you before is that sufficient gradient technique, okay? And so the things that we can then measure once we've measured this collisional thing are the transport coefficients, okay? I've just written one of the more simple transport coefficients to express, but if you've ever looked through the right places of the NRL handbook or you sat through some fusion lectures, you know that these transport coefficients are the game, and you know that they're hard to calculate. They're messy and they all kinds of approximations. But if we can measure them directly, that's great. Okay, and then we can find the true separation of the collisional collisionless physics in the solar wind. Okay, so I'm just going to show you some preliminary measurements by solar orbiter. I'm using trigger mode data, and it's upstream of an interplanetary shock. It just happened to be the data that I was looking at. Okay, so we're coming back to this style of plots from before, um, but I'm not showing the interpolated function this time. I'm just showing the Hermite expansion version. I've truncated the spectrum and returned the function to myself. So here is the result of the drag term and the diffusion term. The collision operator could be in the Rosenbluth form. It could be separated into these two. Not so important, but what is important is the total collisional operator. And so this is again a preliminary measurement of it. I've done these line plots with the slices again, and what you can see is that when you pass through zero, you have a larger effect of the collisional operator. That is exactly what you get when you go through the Spitzer-Harms method of using just a Maxwellian and a delta function. And so the the place that we're at right now is trying to um, employ this technique on lots and lots of data and quantify the effect of collisions through the separation, where the separation in velocity space happens, and start calculating transport coefficients, these kinds of things. So conclusions. We employ a low-pass filter in velocity space to obtain trustworthy VDFs. This is the key to making measurements of kinetic plasma physics processes. And then the ones that I focused on today were a Coburn et al. 2024 paper where we quantify wave-particle interactions through the quasi-linear closure. I went through quite a lot of detail on that. I did not show the preliminary measurements of the field particle correlations. Extra slides if you want to see them. A bit complicated though. And then at the end, I showed you some preliminary measurements on the effect of collisions and measuring the full collisional operator. Thank you.